Okay, what we're going for here is lack of ignorance, right? There are four fundamental forces. So when we said previously that the centrifugal force is not a force, what we mean is that, I mean, A, it's just the tendency of objects to go straight, but B, it's not a fundamental force of the universe, right? There are these four basic fundamental forces, and so let me just talk about them here a little bit, right? And I'm going to start from the weakest, and I'm going to end up with the strongest, right? The first one's gravity. Like me, gravity is always attractive, okay? No matter when you see me, right? I'm always going to be attractive. Um, this is very important, right? Electromagnetic forces sometimes attract, sometimes repel. Gravity is the important shaper of the universe because it's always attractive, no matter what it is, right? Anything that has mass. Okay, so even photons, any matter particle, ordinary matter is attracted by gravity. Even things that are pure energy, like light, gravity acts on them because they have mass. Energy has mass, right? The only thing that gravity can't act on is things like beauty and music and stuff like that, right? Unlike me, though, gravity is very weak. Okay, but it does act on anything that has mass, right? So this is a key concept, right? The next forces, and you can talk about electricity, you can talk about magnetism. Inherently, they're linked in inextricable ways, right? You cannot have a magnet. All magnets are due to the motion of electric charge. Permanent magnets, like iron magnets, are there because the atom itself has a net magnetic moment because the electrons are whizzing around the magnet more clockwise than anti-clockwise or something like that, right? Electromagnets are there because there's electricity. There's electric current flowing in a circle, right? And all electricity comes ultimately from relative motion of magnets and coils of wire and things like that, right? So they're related, right? These things attract and repel, right? So positive charges repel each other, and positive attracts negative, and negatives and all this stuff, right? Right. And then magnets, of course, how do they work? I don't want to talk to no scientist. Anyway, north poles will repel north poles, and north attracts south, and south repels south, and all this stuff, right? So this is true. And then the demonstration that you're missing here because you're in blue pen land is that I very dramatically pick up a paperclip, trombone, with a magnet. Okay, and of course, the paperclip, the Earth is pulling down with all of its six. That's 6 times 10 to the 24th, I think. Is that right? 1, 2, 3, 4. Yeah, there you go. Right? 6 times 10 to the 24th kilograms. It's pulling down with gravity, all of its might. And I take a magnet that has a mass of a gram, and I lift the paperclip up with the magnet. The magnetic force acting up by this magnet is much bigger than the gravity that Earth is exerting, right? So gravity is very weak, but it's always there. It never forgets to act. Ultimately, it crushes stars, and it's a very important force. Okay, electromagnetic forces only act on charged particles, right? So if you're trying to do stuff with neutrons, it's hard to exert an electromagnetic force on neutrons, which have no charge. Okay. Now there are two more forces. Both of these forces act in the nucleus, right? And so they are therefore nuclear forces. Okay? Now, we need a lesson, especially after certain presidencies, right, about how to pronounce nuclear, right? We say new and clear, right? Just say new, clear. It's not a nuclear. It's not nuclear. It's not a nucleus. It's nuclear. Nucleus. Yeah? Nucleus, nuclear. Very good. All right. Now, there are two nuclear forces. These two nuclear forces, one of them is weak and one of them is strong. Now, they appointed a committee to answer, to come up with names for these things, right? They considered names like Charles and Edward and Joanne, right? But they arrived at two different forces, right? They decided to call them the weak nuclear force, and then the strong one they decided to call the strong nuclear force. Okay, I know that's a little bit disappointing, but there it is, right? We're scientists, right? I don't know much about the weak nuclear force. I know that it explains beta decays, which are bizarre. I mean, that's where the nucleus lowers its energy by creating an electron or an antimatter electron could be beta minus or beta plus, right? from pure energy. It creates matter from pure energy, spits it out, right? And the weak nuclear force is used to explain some of these things, right? The strong nuclear force, so I'm all over this, right? This is what binds the nucleus. Remember, in the nucleus, you've got these protons, right? You've got these protons. Here's a helium nucleus. You've got positive, positive, neutral, neutral, right? The neutrons are really the same size, right? Or maybe a wee bit bigger. These guys are bound together. What is holding those positive charges together? Something very, very strong must be holding them together, and it must only act in the nucleus. Okay, therefore, it must be the strong nuclear force, right? When electromagnetic forces act, you have 1 to 10 electron volts of energy. It's just a small unit of energy. When you rearrange atoms, you get 200 million electron volts of energy, right? So this is why atomic bombs are just a bit more strong than chemical bombs, right? It binds the nucleons. It binds proton to proton to proton. It binds proton to neutron. It binds neutron to neutron. Okay? It binds all of these guys together. It's very, very strong, but the reason it doesn't, of course, collapse everything is that it is very short range. So if you get outside the range of the nucleus, which is about 10 to the minus 15th meters, it becomes negligible, right? It doesn't just drop off a little bit. It drops off just dramatically, right? So basically, you have to approach, you have to get these guys together, get them closer, 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 these two positive things, right? If you want to build a nucleus. They repel like crazy, and then at the last minute, right, they will, at the last minute, that, right, they will bond. The strong nuclear force. They have to get very, very close before the strong nuclear force will take over and pull them together. This is why nuclear fusion, where you bring these positively charged things together to release energy, is devilishly difficult to do because the positives repel, right? This repulsion force is so strong, right? But if you get them close enough, then the strong nuclear force takes over. This guy's stronger, hence the name strong nuclear force. Okay, so this is kind of interesting. This is a graph of proton number. So this is atomic number. This is the elements, right? So 20 is calcium, for example, right? Is right about there. Below calcium, and maybe just above that, right? Add a neutron. If you add a neutron, you add a proton. Every time you add a proton, you can add a neutron. All of these dots, every dot is a stable nucleus. Once you get up to about 30 or so, something weird starts to happen. You start adding more neutrons to the atom, right? The reason for this is that the protons are pushing the atom apart. If you have these protons, if you had just all protons, it wouldn't be stable because the protons would have so much force pulling them apart, the strong nuclear force couldn't bind it together. So to make an atom, you have to put neutrons in there like this. Right? You got to sort of water it down. So you got positive, 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 right? And then you've got, maybe you have neutrons in between, right? These guys are neutrons. The neutrons kind of space out the positive charges, make the atom stable. Now, if you look, this thing sort of curves like that, right? It kind of goes, okay? So at some point, you've got to add a lot of neutrons. You've got to add many more neutrons, right? Which is interesting, right? If you split one of these atoms in half, right? If you split this guy in half, you're going to come down here and you need far fewer neutrons. So fission reactions will give off neutrons. This is why they are sustainable. They are started by neutrons and they give off neutrons. This is the atomic bombs, right? Use that idea. Okay, but anyway, back to the main idea here, right? You have to add more neutrons because the neutrons have strong nuclear force, but they don't add that Coulombic force that repels, right? The neutrons are just there to glue it together. They're like nuclear glue. Okay. Now, at some point, on the end there, we think maybe there might be an island out here. We just don't know. Okay. But at some point, you can't get any more in there, and that's because the nucleus. These nuclei are tiny. These guys are right. At some point, these nuclei, this part over here, can't actually act directly on this part. What holds the nucleus together? Well, it's tenuous. Okay, if you've got a big nucleus, this part here, if 10 to the minus 15th is like this big, right? This part acts on this part acts on this part, this part acts on this part. It's kind of like a long human chain. We're all holding hands, right? You know, and ultimately, you're not really. This part doesn't act directly on this part. It's too far away. The strong nuclear force can't act across it. So the atom is loosely. The nucleus is very loosely held together. These giant nuclei, they're all pretty much radioactive. They're not very stable, and the nucleus is not really a solid thing. It's more like an oil drop. It's very oozy. Okay. In fact, the challenge in a nuclear, in a fission reaction, is if you fire a neutron at this oozy nucleus, the challenge is to keep the neutron, stick it to the nucleus. Sometimes the neutrons will just go right through the nucleus and not even stick to it. You got to actually lob it on there slow enough that it sticks to the nucleus. And then, for example, uranium 235 is stable. Uranium, 235 is stable. Uranium 236 is not stable, right? If you try to up it to uranium 236, give it one more neutron, it's not stable. It splits, right? So this is why there's not an infinite number of elements, is that these guys are too big. They're just too big, and at some point, you can't add neutrons, you can't do anything. It's just too big, okay? And so, yeah, there you go. That's the strong nuclear force, short range. Range, how do you spell range? There you go.